In this video, we will do some very basic circuit analysis with Ohm's law. I will show you the passive reference convention, and then we will confirm it by using some circuit simulations using PartSim. So let's get started with a very simple circuit. We have a 5-volt source, and let's make this a 1 kilo ohm resistor. The first important step when you're working with circuits is to recognize the nodes. So we have two unique nodes. I'm going to label them A and B. The 5-volt voltage source tells us one thing right off. It tells us that VAB is 5 volts, which is to say that A is 5 volts higher than B, or we could equivalently say that VBA is negative 5 volts. Now, we're going to use Ohm's law, but to use Ohm's law correctly, we have to use the passive reference convention. The passive reference convention helps us be consistent about our voltage and current and power calculations. If we don't follow it, it's quite easy to get the signs wrong. So first off, the passive reference convention, not the People's Republic of China, dictates that when we have a voltage, we have to use the current that goes through an element from the plus to the minus. So let's write that down. Right? So anytime we're using Ohm's law, we have to be consistent. There's a voltage. Every voltage is defined as having a positive terminal and a negative terminal for the measurement that defines that voltage. And when we calculate current or resistance or power, the current that you're using in the calculation has to go from plus to minus through that element. So let's give you an example. Let's say we wanted to calculate this current. Let's call it IAB, because IAB is flowing from node A to node B through the resistor. Well, the voltage that we have to use because of the passive reference is oriented so that the plus terminal is the entry point on that element and the minus terminal is the exit point. So we'll put here V, and you'll recognize if we were to measure that voltage, which voltage is it? Well, we would put the black probe on the minus terminal and the red probe on the plus terminal like this. And so we have our voltmeter, and you would recognize that this was actually reading voltage VAB. So we'll write this like this, VAB. So Ohm's law, we always say it's V equals IR. Well, that's not very specific because we're not sure about what direction we're talking about here in terms of the voltage and the current, but it has to be because of the passive reference. In this case, it's IAB, and that's going to be paired with V. Okay, so now we know that VAB is VS, which is 5 volts, because we just know that A is 5 volts higher than B. That's what the battery does, that voltage source. We know R. We don't know I, so we can solve for I. So we have 1 milliamp. And just for completeness, I'll note that this is flowing clockwise. It's a clockwise current. Now, let's say we wanted to use the opposite voltage in our calculation. In that case, we would use this as the observation voltage and this as the minus voltage. But now we can't use IAB. We would have to use the current that flows in this direction. We could call that IBA, which we could recognize as negative IAB. So the voltage that we have to use in this calculation, if we're going to use the passive reference convention, is the voltage defined with this positive and that negative. So that is actually VBA. So now you can see, for example, let's calculate IBA and we'll use VBA. Well, we know that VBA is negative 5 volts because A is 5 volts higher than B, so B is negative 5 volts higher than A. So to put it in Ohm's law, we'd put VBA is equal to IBA times R. Again, the passive reference making the current that we use be the one that goes from plus to minus through the element, through the resistor of interest. Now we can calculate IBA because we know R and we know VBA. So we end up with negative 1 milliamps flowing counterclockwise. And notice that what we've achieved here is completely consistent. IBA is negative 1 milliamp flowing counterclockwise, and IAB is 1 milliamp flowing clockwise. These two are exactly equivalent. Now, let's simulate this in PartSim. Briefly, I'll sketch the way I'm going to set it up. So what I'll do is I'll insert 4 ammeters. So in the circuit simulation, this first one is measuring current that flows from A to B, which is clockwise. That's the current goes here and then flows this way. But the next ammeter is measuring current that flows in the opposite direction. This current flowing counterclockwise through the circuit is IBA. Again, if we call this A and B as before. So let's call this 1 and 1. And then this first ammeter is measuring the current that flows like this. It's clockwise, so it's IAB. And the second one is measuring the current that flows counterclockwise, IBA. So let's call this 2 and IAB2. So to put this in a circuit, we're going to use an ammeter. And in PartSim, the ammeter looks like this. A for ammeter, and then there's a plus and a minus side that indicate the red and the black probe leads. So for the second ammeter, it'll go in the circuit like this. So we'll just build that now in PartSim, and we'll take the measurements and we'll simulate it. So here is PartSim. It's free, and the nice thing about it is you can just use it. So to make our circuit, we're going to go to the generic parts, and we'll take out a passive element. That's how you get a resistor. Click, and then click to position it. And it's already 1 kilo ohm, as in our example. Now we need a voltage source. So we click Sources. We get a DC voltage source. And if I want, I can move it over a little bit more. So let's just click on this, and we get this menu on the side. So I'll put in here that I want 5 volts. It's going to be designated V1. That's fine. Now we need test equipment for the ammeters. So here's an ammeter. We'll rotate it. Right click. I can rotate it like this, and then I will flip horizontally. I click from the end of one component to the end of the next. And let's put in another ammeter going the other direction. I'm going to rename this one. Instead of M1, I'll call it IAB1. The next one will be M for meter, and then put IBA2. We'll connect these just like in the circuit that I defined. Add a couple more meters. I can also copy and paste. So let's copy, paste. We'll rename these IBA2. No, this is IAB2 because it's measuring clockwise current, and then this is going to be IBA2. So this is a very nice simulation tool. Let's also add voltmeters. This voltmeter is going to measure VAB, that is. So let's give it that name. This is the meter for VAB. And then another voltmeter, let's invert it. And we're connecting it to nodes A and B in the opposite polarity as VAB. So this is going to be given the label VBA. Okay, one unrealistic thing about PartSim is that in order to run a calculation, you need a ground. So you get that from the ports section here under generic parts. There's a ground. And it doesn't matter what node you connect this to, because the ground really is just an arbitrary and artificial reference, which we call the zero of potential, zero of voltage. You can pick any ground in the circuit to be 0, but you only get to do it once. And so I pick that one. Now I can click run, and it may seem like overkill, but let's do that again. Run. I don't want the DC bias. Instead, I'm going to get the transient response. This is going to seem like overkill, especially for such an easy circuit and a DC circuit, but this is the only way to treat the ammeters in the most realistic way. So I hit run, and it gives me the output here. So it's showing me IAB2 and IBA2. What you see here is that they're consistent. So IBA2 is negative 5 milliamps, whereas IAB1 is 5 milliamps. And how does that square with what we have analyzed in our circuit? Well, we analyzed earlier that if this is 1 kilo ohm, it's 5 milliamps going like this. That is to say that IAB is 5 milliamps. In fact, that's IAB1. And IBA1 then has to be negative 5 milliamps. IAB2, it's clockwise, so it's 5 milliamps. IBA2, counterclockwise, negative 5 milliamps. So that's what we're seeing here. The current IAB1 and IAB2 both are 5 milliamps. Down here, the other two, IBA2, and maybe we can see the IBA1, but I can't at the moment. The currents that we measured are consistent with our work in the passive reference convention.